Have you ever wondered how far a cannonball can fly from a cannon set on a certain angle, or how far a kicked football can fly? Well, one way to look at it is just pull a tape measure and measure it. Or in case of a cannonball, pull a really long tape measure. And that's really one way to look at it. Another way is to calculate it. If it's really inconvenient to measure, you can calculate predictably how far objects will fly through the air. And this certainly applies to bullets and arrows, stones and thrown across the air and those kind of things. So what we need for this calculation is we need to determine distance, d for distance. Now to calculate distance we need speed and we need time. So you either measure distance or you calculate it. And to calculate it, you're gonna need time and you're gonna need speed. Say, before we calculate this one, there's one more concept that you need to be refreshed on. The direction of motion. And let me just draw you a simple situation. Say, here is an observer standing there. This is a road and that box now is a car. If this car is traveling at a certain speed, say 10 miles per hour in that direction, all the speed, all the effort is being exerted in the direction of motion or displacement. Motion, or otherwise known as displacement. Okay, when a car is just going along a road, pretty straightforward. Now, same from the point of view, from the observer's point of view, the car hasn't gone up, hasn't gone down, it only got further away. Straightforward business. Here is the same observer there, and we've got an elevator cabin that's being pulled up by a cable, or a bucket of mortar. It doesn't matter if the bucket of mortar or elevator cabin is rising at a speed of, I don't know, 1 foot per second, then the observer can confirm that indeed the bucket is rising vertically at 1 foot per second speed, and can also confirm that the bucket in relation to vertical movement, in relation to horizontal movement, it hasn't moved an inch from this spot. It's only being lifted up or lowered down. It hasn't moved from this spot. Back to the car, same thing. From this point of view, it hasn't moved an inch. It only moved horizontally in the direction of displacement. Same for the bucket of mortar. It moves in the direction of displacement, but it doesn't move from the other point of view. Now, when you are driving this car up on a hill, let's see, how do we do this? Here is horizontal, and I'm just gonna write H for horizontal, and this is V for vertical. That's not velocity, that's now vertical and horizontal. And you've got an uphill there, and on top of the hill you got a car park here happening. And there is your sign for a car park, and you are driving a car up the hill. If you are observing it from here, the displacement, you say you're going up the hill at 3 kilometers per hour speed, really casual. The displacement does happen in both directions. It's both the horizontal and the vertical displacement. and the effort is being exerted neither horizontally nor vertically, but somewhere in between. Okay, and the resultant displacement will make the car move along. Say if this started here at 0, 0, after a certain amount of time it will have some horizontal displacement and some vertical displacement, and after another certain amount of time it will have more horizontal displacement and some more vertical displacement at the same time. And when it's up on the top of the hill, it's gonna have even more horizontal displacement and even more vertical displacement than ever before. Okay, and same situation is happening to a projectile shot at an angle. Say if a bullet leaves on a trajectory like that, it's both rising and moving ahead horizontally, and after a while it's gonna come back, and we're trying to calculate this distance. But the bullet's initial speed is spent, some of this speed, some of the effort of the bullet, that's a bullet now, some of the effort of the bullet has been spent on lifting it up to a certain height. First it goes to this height, and this is a horizontal, to this height and to this distance, and then it's here, and it covers this much distance and this much height, and then it's halfway through its travel and it rises to this height and goes this much distance, and so on. It covers more ground, but then it's losing some altitude and covers more ground, and it's losing some more altitude. So it's important that you understand that some of the bullet's speed is being spent on moving it horizontally, and some other part of the effort that it's exerting is being spent on moving it up vertically. To calculate it in math, we're back to sine, cosine, and trigonometry. Say if we have a situation where a bullet is fired at a really shallow angle, it's gonna have 1 unit of vertical rise and, I don't know, 2, 4, 6, 8, 9 units of horizontal run. Only 1 unit of vertical rise is being no, the other way around. From some of its effort that it's exerting, from some of its speed, only a very little fraction is being used for elevating the bullet. If the bullet is shot up nearly vertically, most of the effort that the bullet is subject to, most of the force is being spent on changing the bullet's altitude, and then it's gonna drop back down on the ground about yay so. Okay, and very little of the bullet's energy is spent on making it go forward in a horizontal direction. So let's do some calculation now. I'll show you how we do this with sine and cosine. So if we have a triangle like that, and this is the hypotenuse, I'm just gonna write hypotenuse, and this is an angle that I want to reference everything by. Then this is the side opposite to the angle, and this is the side adjacent to the angle. If I want to calculate how much of a bullet's speed is being spent on elevating the bullet, I'm gonna need to solve it for O, for opposite side, because this is the one that's describing how much of the bullet's total speed is being spent on elevating. And opposite equals, well, let's just go back to sorry, we've got so, ka, and TOA, and if I need the vertical side to be solved, then I'm gonna have to use the hypotenuse times sine of this angle. This angle is important there. This one is a Greek letter theta, okay, and it's just a zero with a wavy line across. So you have to have an angle and you have to have a height. Sorry, not the height, hypotenuse. The hypotenuse is, I'm gonna change it in just a sec. And if you want to calculate how much distance it covered, that's gonna be hypotenuse times cosine, whatever angle the bullet is being fired at. Now, let's see some numbers. If a bullet is going up on a, I don't know, 22-degree angle at 200 meter per sec speed, then that means that the bullet is rising at how do I write it? Say vertical velocity vertical. Okay, that's velocity vertical equals 200 times sine what angle? 22 degrees. 200 times sine 22, and it's 74.9. I'm just gonna write 75 meter per sec, because 22 degrees is a fairly shallow angle. Not much of the bullet's initial speed is being spent on lifting the bullet up away from the ground, but it is coming up at a rate of 75 meters per second. And horizontally, velocity horizontal is 200 times cosine 22 degrees, and is 185 meter per sec. Now 185 and 75 do not add up to be 200. Don't worry about it. That's normal. Okay? That's how you work with trigonometry. Let's do one more. Where do I put it? I put it there. If a bullet is fired up at, I don't know, 72-degree angle from the ground and has a muzzle velocity of velocity initial is I don't know, 2000 feet per second, then the calculation is for velocity vertical is 2000 is velocity initial times sine whatever angle, which gives us 2000 multiplied by sine 72 equals 1902 feet per second speed is going to be spent on raising the bullet and elevating it. For horizontal displacement, it's the initial speed times cosine of the angle, which is 2000 multiplied by cosine 72 equals 618 feet per second. So the bullet is only going horizontally 618 feet per second. Say we know that the maximum range can be created when the bullet is fired up exactly at a 45-degree angle, like so. Because at a 90-degree triangle, we know that this leg of the triangle is exactly as long as this leg of the triangle, so the bullet's speed or energy is spent half and half for traveling both horizontally and vertically. say the muzzle velocity of an arrow is 27 meters per second. That's velocity initial equals 27 meters per sec, and it's going up on a 45-degree angle. So velocity horizontal is velocity initial times cosine 45, which is cosine 45 multiplied by 27 equals 19 meter per sec, and the velocity vertical, sorry guys, that's ugly now, but velocity vertical equals velocity initial times sine 45 degrees, and that gives us 27 multiplied by sine 45, 19 meter per sec. Alas, calculation confirms that the horizontal and the vertical travels are the same, 19 meters per sec in both directions. And like I said, they don't have to be adding up to 27. What they need to be doing is going back to a Pythagorean theorem. 19 squared plus 19 squared should equal 27 squared. It should check out. Let's see. Oopsie, wrong button. Square root bracket 19 squared times 2 bracket equals, yep, we've got 27, pretty close, 26.8, but I was ignoring some decimal digits, that's why we didn't get exactly 27 back, only 26.87. So 19 checks out and 19 checks out. I was just rounding it down a little bit. So the maximum range is happening at a 45-degree angle. Now, once we have horizontal and vertical speeds, we can calculate distance. We also need one more thing: flight time or hang time. Flight time. Oopsie, flight time. And for flight time, we're going to use another equation. I'm going to cut to the chase. The flight time will be calculated as 2 times the velocity, the vertical velocity, divided by the gravitational pull of the Earth. That's the total flight time a bullet spans from initial position where it's that's a handgun, where it's being fired and goes up, and then it comes down, and there's your max range. Max range from there to there. So to calculate the time, 2 times the velocity vertical divided by the gravitational pull of the Earth. So we have vertical velocity here, 19 meters a sec. So 2 times 19 divided by 9.8, because the gravitational constant is 9.8 meters per second square. So we have 2 times 19 divided by 9.8 equals 3.877 seconds. So the flight time is 3.877 seconds. And what we do now is we've got time here. Sorry, wrong bubble guys, not that one. We've got time here, and we've got speed here. I'm intentionally pointing and circling the horizontal speed. However, the vertical speed is the same, but keep in mind, if it's not on a 45-degree angle, you're still gonna have to use the horizontal speed, okay? So that's why I'm circling that one. So use the horizontal speed and the flight time, and what you do is distance equals speed multiplied by time, which gives us, here is the 3.877 still on the display, multiplied by 19 equals a 73.6 meter maximum range for an arrow that's being shot at 27 meters per second initial speed. That's how you calculate maximum range. And if you're thinking, well, heavier bullets will hit the ground sooner, yes and no. The mass of an object is being factored into its initial speed. The heavier things will creep out of the barrel slower, and the lighter things will go lightning fast. Okay, so yes, mass is important, and this is where mass is being factored in. It's part of the initial speed the bullet can reach. Okay, so don't get carried away. You can watch it again and again, and that's how we calculate maximum range of a projectile.